Hi, we're going to look at net and total ionic equations now. So I've written a new example. It's very similar to number 9 in your workbook. So you see number 9 on the screen right now. There's a number of examples there in the book. And I've written a new example similar to that. So I'm leaving the ones in the workbook for you to practice. You're going to complete and balance, so a little bit more work to do here than in the workbook question. And you're going to write the total and net ionic equations. So when we examine this reaction, we see that it is a double displacement neutralization type reaction. So I know that the ions switch pairs, the potassiums go with the phosphates and the hydrogens go with the hydroxides. So depending on your perspective, it's not a true double displacement, but it sort of follows the same pattern. So some people consider it a double displacement and some don't. It all depends on how you look at it. So potassium will pair with phosphate, but we know that potassium is a 1 positive, and when we check the charge on phosphate, it's a 3 negative. So the correct formula should be K3PO4. And we check our solubility rules, and we find that that is a soluble compound. Phosphates are not normally soluble, but they are with the 1A cations. So this will be aqueous, and the hydrogen from the acid, the phosphoric acid, meets with the hydroxide from the base, and we get the second product is water, and that is a liquid. And then we need to balance the reaction. So we're going to need a 3 to balance our potassiums. We're going to need, so we have 3 hydroxide and 3 hydrogen, making 3 water. We have 3 potassium, 1 in front of here, and 1 in front of here, and everything is balanced. Now, in order to write the total ionic equation, it's necessary to separate into ions anything which does separate into ions. And there are only 2 things that do: soluble ionic compounds and acids. All others do not separate into ions. Soluble ionic will separate into ions, but insoluble will not. Covalent compounds generally do not separate into their ions unless they are acids. And elements don't break into ions. So the only thing I'm breaking is soluble ionic. And here I see a soluble ionic compound. So I'm going to break it into ions. There will be 3 potassium ions, aqueous, and 3 hydroxide ions, aqueous. The next compound is an acid. Acids are broken into ions. They exist in the form of ions in water. So 3 hydrogen ions and a phosphate 3 negative aqueous. The next thing that I see on the product side is a soluble ionic compound. So I break it into ions. So I have 3 K positive aqueous and a PO4 3 negative aqueous. And the final thing that I see is water, and water is a covalent compound. It's neither a soluble ionic nor an acid, so I leave it alone. I write it in exactly the same form, its molecular form. Now the next thing is to look for spectator ions. Spectator ions are things which are identical on the left and right hand side. They have to exist in exactly the same form. They're always ions. There will be the same number, same charge, and same physical state. So potassium is a spectator ion, And the second spectator ion is phosphate. They're completely unchanged. You're a spectator that watches the reaction happen and nothing more. So I have 3 hydroxide and 3 hydrogen producing 3 water. When we get to this step, if the coefficients can be simplified, and I see that they can, we can divide these numbers by 3. We write it in simplest terms. It's kind of like reducing a fraction. You don't have to rewrite it in this order. I'm just accustomed to seeing it this way, so to me it makes sense to have the positive before the negative, but it's absolutely not required. You could have written hydroxide plus hydrogen, that would have been fine. And there is your net ionic equation for this reaction. For the second reaction, it looks like a possible double displacement. When I repair my ions, I know that this is a nickel 2 because it required 2 chloride 1 positives, 2 chloride 1 negatives to balance it. So the nickel 2 is going to require 2 hydroxide to balance. And the other pairing of ions is lithium with chloride, so LiCl, 1 positive, 1 negative, 1 of each. Now you need to use your solubility rules, and you need to check these. Chlorides are usually soluble. Lithium is not an exception, so this one is AQ. We know in this type of double displacement, if it's not a neutralization and we don't see a precipitate, then there's no reaction. So there should be a precipitate here. When we check hydroxides, hydroxides are usually insoluble, except for when they're with group 1, strontium, barium, and ammonium. So nickel 2 is not listed here. It is in fact insoluble, a solid, so I write S. Now I need to balance my equation. I'm going to need 2 in front of here to balance the chlorine, and also I'm going to need 2 here, which balances both the lithium here and the hydroxide here. Now, it's the same thing again. We're looking for soluble ionic equations. Sorry, this should have been a given. We're looking for soluble ionic compounds, and this is soluble and ionic, so we're going to write it in the form of ions Ni2 positive aqueous and 2Cl negative aqueous. The lithium hydroxide is soluble and ionic, so I have 2Li positive aqueous and 2OH negative aqueous. Don't forget, in 2 lithium hydroxides, we would have 2 of each of these ions. Very common for people to forget to put the 2 on the second ion here. On the product side, this compound is not a soluble ionic because it is insoluble. So I have to write it again in its original form, 1NiOH bracket 2 solid, which did not separate, and the final compound is a soluble and it is ionic. So I break it into ions 2Li plus aqueous and 2Cl negative aqueous. Now again, in order to write the net ionic equation, I am looking for spectator ions, things which are identical. So lithium is identical on both sides, Li1 positive, and so is the chloride ion. The nickel is not identical. It's an ion on this form, and it's part of a compound and neutral over here. And the hydroxide, again, is outside of a compound. It's a free ion in solution here, but it's bound inside of a solid here. Remember, spectator ions are there are ions on each side, just like the name implies. If I write down what's left, Ni2 plus aqueous and 2 hydroxide, 1 negative aqueous will produce nickel, nickel 2 hydroxide solid. And this cannot be simplified any further. I can't reduce those coefficients, so I am done. That is the net ionic equation. So these are a couple of typical ones. The first one was an acid-base neutralization. The second one was a precipitate formation. They're typical. You can also have a net and total ionic equation for a single replacement reaction as well, but they're typically used for double displacement reactions in solution.